Hello, Yaneli. Good afternoon. That was fast. Oh, I saw that Yaneli response fast. Uh, okay. Good afternoon, Brian. Good afternoon. Good afternoon, Kaya, with the double and the fast. Good afternoon, Yaneli, with the double. Yeah, with the total double, with the triple in a way. Good afternoon, Chastity, with the double. Good afternoon, Kaya, with the double. Good afternoon, Natalie. Good afternoon, Genesis. Good afternoon, Aria. Oh, Gabriella. There's Gabriella. Oh, with the double, with the triple, with the wave. There's going to be a portal for waves. All right. Um, yes. Good afternoon. Thank you for your service. Good afternoon, Ariana. Good afternoon, direct chat person. And good afternoon, Gabriella with the triple. Okay. Um, the hat trick. Okay. Good afternoon, everyone. Who did I know? And Mariam, if I didn't say. Okay. Um, we are going to let that person in from the waiting. We are okay. Um, I want to spend one more day on the Doppler effect. Well, we need to spend one more day on the Doppler effect. Uh, oh, a quick question. In this section, in your section, remind me, please, did you guys, people, have a board meeting about the Doppler effect in your lab section? Like, has that sometimes that happens and sometimes it doesn't. There's no correct answer. I mean, but I just want to know. Not yet. Okay. Thank you, Brian, and thank you, direct chat people. And no, we haven't. No, we haven't. No, well, this is an interesting thing too. In the other class, okay, good. So some of you just wrote not yet, and this happened in the other section too. Just out of curiosity, when you say not yet, is that because you're being polite, like because you just assume if I'm raising the question that presumably it's going to happen, or did the lab instructor actually like mention that this is something that's going to happen? Like, do you know for a fact? Because sometimes people don't even do it. I mean, it sort of varies from some. So, have you actually heard from anybody? Have you ever heard of that from anybody other than me of whether there's a board? Oh, okay, you assume because I said it. No, that's totally fair, and I appreciate it. All right, all right, all right. And so you might, but you might not. So I'm not promising you that you will. Sometimes, and frankly, I guess if it came to it, probably you'd probably rather have a review session about your midterm. I mean, not that it's up anyway. Okay, okay. So you have not. Therefore, it is all the more reason in my mind that we have one more class on the concept of the Doppler effect, because it's very important. It is something you need to know. It's an important concept in physics. It's a very familiar phenomenon and an important phenomenon in real life. Like even, I mean, you've heard of like Doppler radar, weather reports and stuff. Like people in the world know about Doppler. It does have far-reaching implications. That's one of the many reasons I like to focus on it for a bit in the middle of this class. But then also the problem solving technique, the computation that one does, that I do, in order to solve for the different cases, is a computation technique that I think is very representative. It embodies a lot of physics principles that I want you to know. Um, so today we're going to spend just one more day trying to practice it. Like I've mentioned, on either the midterm exam or somewhere on one of your exams, always there is a big Doppler effect problem. Like we're not just spinning our wheels here. There's always a big problem about the Doppler effect. Um, on one of the two exams, um, and your main responsibility in that big Doppler effect problem is to be able to analyze each of the four cases, to analyze them with the same computational method, but to see and be able to understand why that same computational method will yield some different results for the four cases. So your ultimate responsibility is to be able to understand, to compare and contrast the four cases of the Doppler effect. One of which we've already done together as a group. On Monday, we've done one. I'm not going to walk through all four with you. I want you eventually to get the point and be able to do all four on your own. But we are going to do one more case today for the purpose of compare and contrast. Okay. And we're going to do them like as soon as I stop talking, you're going to do the next case in breakout rooms together. You're going to make a prediction. You're going to do the computation as practice. You're certainly going to look at your notes from Monday. Like you're going to try to follow the same model we did Monday in one case to solve for the numbers for a different case. That's what you're going to do today, but we're going to do it soon enough to have enough time to come back and for me to show you the result, make sure we're all on the same page, etc. And bear in mind, like partly you're just practicing. You're practicing, can I solve a Doppler effect problem? But also the goal is you're sort of trying to collect these cases in your mind or in your notes. You ultimately want to be able to sort of stand back and look at the four cases and make sense physically as to why the numbers are similar or different in the way that they are, like what the numbers mean. Okay, so we're going to do that in a few minutes. We're going to do another case of the Doppler effect. Now, also, by the way, in theory, I think 2 weeks ago, I think Monday of last week, in the other group, I think I quickly did yet a different case, but I did it very quickly, and then you watched the video of it. So, in theory, by the time we're done today, I believe that in your notes, one way or another, you would have the results of three different of the cases, and the only one that's like missing is the fourth. And all of that together constitutes homework 4. Homework 4 is the sheet is terribly written. I apologize. Like I need to change the sheet. The sheet is like very hard to understand. That's not on purpose. It just happened a long time ago. But the summary of the sheet is that you're trying to get four distinct answers that may or may not. Some of them might be the same. But you're trying to get four different answers for the four different cases. That's the point of homework 4. So just to be clear, like what we're doing as a group is we will have gotten the answers to 3 out of 4 of those cases by the end of today. I don't even remember when the homework was due or what, but certainly if you turned in a draft on time, you're welcome, of course, to use anything that we've done in class to fix your homework and re-upload it, and get all the points and all of that. And I'm so behind right now in giving you stuff that I certainly wouldn't bother. You certainly wouldn't be behind if you did that. Okay, so shortly, and stop me if I'm not making any sense, but shortly, that's what's going to happen. I'm going to turn it to you in breakout rooms to solve a different case of the Doppler effect from the one we solved on Monday. However, wait, I'm looking at the chat. Okay. However, before we do that, I'm going to talk in space for a second. Like I would encourage you to take notes on what I'm about to say. I'm not going to write it down myself because then we'll never get to the example. But I keep saying that you need to be able to solve different cases of the Doppler effect. Let me remind you, first of all, that solving, what I mean by solving, hang on. I mean solving for F sub WR. So what you're always, in any Doppler effect problem, the thing you're looking to solve for is FWR, meaning the frequency of the wave relative to the receiver. That is the goal of every Doppler effect problem, of every case of the Doppler effect. That is the assumption of the Doppler effect. The whole situation of the Doppler effect is that something sends a wave to something else, right? Something that we call a source sends a wave to something that we call a receiver, right? Like a pitcher and a catcher of a wave. Could be any kind of wave. We're here focusing on sound waves because they're so familiar and so real, right? But it could be any wave. So you have a source of a wave and you have a receiver of a wave. The situation of the Doppler effect always, so I'm just briefly summarizing now. The situation of the Doppler effect always is that either the source or the receiver has a non-zero velocity relative to the wave medium, right? Like a Doppler effect occurs when either the source of a wave or the receiver for a wave or both is moving relative to the medium for that wave. If either one is not in the same reference frame as the medium for that wave, then ultimately what occurs is that the receiver and the source will have different measurements for the frequency of that wave. Like the condition of the Doppler effect is that something is moving relative to the medium. The result of the Doppler effect, the effect itself of the Doppler effect, the effect is that there will be a disagreement regarding wave frequency. Like one wave will have its frequency measured as one thing by the source and as a different number by the receiver. That's the result of the Doppler effect always. And and both measurements are equally correct. It's not like one is an illusion or a misperception or like or something like that. Both are totally legitimate measurements in the same way that two different velocity measurements made in two different frames of reference are equally legitimate velocity measurements, right? This whole okay, so that's what the Doppler effect is. So what's always happening in every Doppler effect problem is you're given a bunch of information, such as the speed, the velocity of the wave relative to the medium, the frequency of the wave relative to the source, and then the velocity of something relative to the medium, either the source or the receiver. And from those pieces of information, you solve for the frequency of the wave relative to the receiver. And the whole point is that it won't be the same as the frequency of the wave relative to the source, right? Again, that's just like a summary of what's happening in every one of these problems. I do want to make this, and again, in a way, in a minute, you're going to practice the math of that, like in breakout rooms in a minute. But because we're spending so much time on it, which we always do, because I make such a big deal of it, I kind of want to defend that to you for a minute, or like I want to give you a small taste of like why this is so important. Well, first of all, in terms of daily life, I think we all agree this is a common experience. I mean, all the math that we're doing right now, if we're doing it in the case of sound, right? This is the experience of you're standing on the street corner in New York City and a motorcycle passes you by, right? It comes toward you and then goes away from you. And so what you hear is something like, what you hear is something like, I mean, like, yeah. But right, like, let's be clear. The Doppler effect is when the motorcycle comes towards you and then goes away from you. What you hear is something like, Now that's really something like that. Let me be very specific. I'm talking about a motorcycle or car or whatever, but what I'm not talking about is a siren. Like that, I'm talking about something that's, say a motorcycle is blaring its horn, is just making one continuous sound, one note according to it. A situation where if you were sitting in the motorcycle, you're just hearing, right? Like, by the way, it doesn't even have to be its horn. I mean, it could be its engine or whatever. But if you imagine that there's some source, like a motorcycle, that's emitting a frequency, that's making a sound, that is from its frame of reference, constant sound, a certain pitch. I'm saying that when the motorcycle's coming toward you, that is one case of the Doppler effect. In fact, specifically, I believe that's literally the case that we analyzed 2 days ago, Monday, right? That is the case of source approach, right? The source of the sound is coming toward you, you being the receiver, right? So while the source is coming toward you, you hear a note that is higher than the note that the motorcycle hears, right? Now, right, like the motorcycle might hear like but you hear or whatever, right? And by the way, the difference is more dramatic the faster the motorcycle's traveling compared to air, right? So while it's going toward you, you hear a sound that is higher than what it hears. Now, here's something I want you to write down what I'm about to say. Again, I don't want to like get involved in the different boards and rabbit hole myself, but I want you to write down part of what I'm trying to illustrate with this common everyday example is number one, like so comments on Doppler effect. Like number one, notice the effect has to do the effect involves pitch, not volume. The first point I just want to make is all of this stuff is about frequency at the end of the day. This has nothing to do with volume. Okay, so like say that however you want in yours, but for sure, a motorcycle that's coming closer and closer to you, sure, I'm sure the sound gets louder and louder as the motorcycle gets closer to you. Like that is true, but that has nothing to do with, that's just true of waves in general. That like, it doesn't matter how fast they're going or anything like that. And it doesn't matter about relativity or anything like that. That's a whole different issue. That's true no matter what. So anything I'm talking about the Doppler effect, I'm talking about the note that you hear, not how loud it is. That's number one. So okay, yeah, that's number one. Number two, the Doppler effect involves or is depends on velocity, not position. Okay, so number one, the Doppler effect involves frequency, not volume. It involves frequency, not amplitude, or it involves pitch, not volume. Same point. And number two, the Doppler effect depends on velocity, not position. So I'm saying when the motorcycle's coming closer and closer to you, like when the motorcycle's approaching you, I don't care where the motorcycle is. That doesn't have anything to do with any. I mean, what that has to do with is how loud it is, but that's not the Doppler effect. Where the motorcycle is does not change the pitch of the sound coming out of the motorcycle. What affects how you hear the pitch is how fast the motorcycle is going. So if the motorcycle is coming toward you at a constant speed, right, you're going to hear a constant pitch. And frankly, while the thing is coming toward you, there's nothing about it that seems Dopplerish to you, right? You're just going to hear a note that happens to be higher than the note that the motorcycle driver hears, but you can't hear what the motorcycle hears. You can only hear what you hear. So you don't know that, right? So the motorcycle, like unless you both had tape recorders or whatever, like iPhones, and then you set them down next to each other later on, which would work. But while the motorcycle is coming toward you, it hears and you hear right? That's case one of the, and it doesn't matter how close it gets, or whatever. It's just the same. Sorry, that wasn't it, but you know what I mean. Then the motorcycle gets to you, and it doesn't have to literally get to you. I mean, it could be like way over there, but I mean, once the motorcycle like passes the line that you're standing on, and once it passes that threshold, so that the motorcycle is now going away from you. Now it's a different case of the Doppler effect. Right? That's what I'm sort of trying to argue. Is like that was case one, source approach. Now it's a different case. Source recede. Now the motorcycle's going away from you. So now it's like it's like you being at the beach, running away from water waves at Coney Island. Like if you run away from them, they're going to slam you in the body less often than if you just stood still, and which is itself less often than if you ran into them, right? Hopefully you can picture that. I mean, in the end of the day, if things are approaching each other with waves in between, then frequency is higher for the receiver than the source. But if things are receding from each other, then the frequency is lower for the receiver than the source. So I'm saying when the motorcycle passes you, the Doppler effect that you experience is actually a change from one Doppler effect case to another. So if you were to make a graph of like, here's like where the motorcycle is mapped on the x-axis, let's say, and the frequency that you hear, say, is on the y-axis, what you would hear is something like and and right, and that drop is right when the motorcycle passes you. And when I say you hear in between those two lines would be an x-axis, right? Like one of those notes would be above the x-axis, let's say, or would be above an equilibrium value, and the other would be below that value. And what is that value? That value would be what the motorcycle would hear. Do you follow me? Which is not, again, which is not any more correct than what you're hearing, but it would be constant. The motorcycle would never experience anything. Now, right? So the motorcycle, oh, okay. So the motorcycle the whole time is, and you go, you understand what I'm saying, I think. And now that would be two cases of the Doppler effect. The other two would be if that entire situation were going on, except you were yelling at the motorcycle, right? If you're yelling at the motorcycle, is that what I mean to say? Yeah, that's what I mean to say. If you're yelling, but like if you're singing, you have a pitch pipe or a harmonica or something, you're going, whoa, to the motorcycle. Well, the motorcyclist would experience everything I just said, only presumably. Wait, is that what I mean to say? Oh, yeah, that's totally what I mean to say. Right. So then the motorcycle would experience everything I just said, and that would be the other two cases of their Doppler effect. Okay. Why does this happen? I'm looking at the time. Okay. Why does it happen? Just to remind you again, and I'm going to say it conceptually, but then hopefully when you do the computation, you can see it in the computation. The whole reason this is happening is in effect because of what's written on the board right here, plus Galileo's principle of relativity. Like what's written on the board here is the nature of waves. Like the big thing that's emphasized here is well, ignore that for a minute. The thing under the big thing, it says VWM. It looks like a lot of gobbledygook, but it's just three. If you look under the big lambdas, there's three equations here. It looks all like gibberish, but it's three equations, and they're really the same one equation written from three different perspectives. It says VWM equals lambda WM times FWM. Right? Block out the subscripts in your mind for a second. It's just saying V equals lambda F. That's true of any wave. V equals lambda F. The speed of a wave is its wavelength times its frequency. I mean, that is something that's going to come up again and again in PChem, I promise you, and instrumental. The speed of any wave is its wavelength times its frequency. You can memorize that if you want, or you will accidentally, but you can also understand that's just a way of saying speed equals distance per time for a wave, really. So the speed of a wave is its wavelength times its frequency. But then why I'm writing it with all these subscripts in three different ways is I'm trying to emphasize, okay, the speed of a wave is its wavelength times its frequency. But the thing is, for a wave, for everything in physics, speed, velocity is relative. It's always a relation, a comparison between two objects. With a wave, the most obvious, most relevant comparison is the speed of the wave compared to its medium, because that's the speed that is fixed. Like that's what we were sort of learning Monday and last week. Like my big point about waves, the big exciting discovery or finding about waves is that once you define that you can't, a wave is a wiggle. You can't have a wiggle without things wiggling. So you can't have a wave without a medium. Once you define the medium, once you say, aha, it's water molecules that are shaking back and forth like masses on springs, or once you say, aha, it's air molecules oscillating back and forth in the manner of masses on springs. Once you define what your medium is, then you automatically know the rate at which pulses will propagate through that medium. So the speed of a wave relative to its medium is equal to the wavelength of the wave relative to the medium times the frequency of the wave relative to the medium. But then that's what the first of the three gibbery equations look like, says. But then I'm saying, but you see, velocity is relative, right? It's always a comparison, and all comparisons are equally valid as long as they're self-consistent. So as in the same way that we could say the speed of a wave relative to its medium is the wavelength of a wave relative to the medium times the frequency of the wave relative to the medium, we could shift perspective and look at the whole thing from the perspective of the source and say that the velocity of the wave relative to source is equal to the wavelength of the wave relative to source. Oh, and that's a typo. No wonder nobody understands what I'm talking about. Hold on. This is supposed to be that. Okay. The frequency of a wave relative to the source, right? Or third equation, they're all the same equation. I'm just like looking at it from different perspectives. Or I could say the velocity of the wave relative to the receiver equals the wavelength of the wave relative to the receiver times the frequency of the wave relative to the receiver, right? It's like everything in physics, like it looks like garbage until like you start cleaning it up and then you realize, oh, I kind of knew this the whole time. I just didn't know that it mattered. Um, right. So I'm saying the velocity of a wave in any frame of reference is the wavelength of the wave times the frequency of the wave. But, oh, and I'm saying the velocity of a wave relative to its medium is like known from the start once you know what wave you're talking about. But then I'm saying, so what happens in the Doppler effect is even though so let's talk about sound, the motorcycle thing, even though everybody will agree that the speed of sound is 340 meters per second, what they're agreeing is that sound travels 340 meters per second relative to air. That's what we're all agreeing. That's what we all know in advance. We know BWM. We know that the speed of sound, and that's like amazing that we can know that because then that means what that means is if someone is moving relative to the air, or same idea, if the air is moving relative to them, then they won't agree to that number. They won't measure that number. They won't experience that number, right? The motorcycle that is coming toward you, if it's coming toward you at 40 meters per second relative to air, like it's cutting through the air that way, then sure, in the motorcyclist's brain, they can agree with the fact that sound travels at 300 meters per second relative, 340 meters per second relative to air. But they're cutting through the air. They're experiencing wind. They're having the air come toward them like this. So literally by every measurement, by every physical way of verifying anything practical, like they're experiencing a sound that every second the sound is getting 340 meters ahead in the box of air, while the air comes back by 40 meters by the whole box of it's not literally a box, but you know what I'm saying? Like the whole clump of air comes back by 40 meters. So every second, as far as the motorcyclist's reality is concerned, the sound is only 300 meters ahead of the motorcyclist. Like that's very important. What I'm saying is that a source or a receiver will disagree on the speed of a wave if either one of them is moving through the medium or the medium is moving past them. And so I'm almost done with this. Again, this is just like the summary, the review of what's happening conceptually. If either the source or the receiver is moving relative to the medium, then the source and the receiver of a wave will disagree. Their measurements will differ on the velocity of the wave, like relative to them. They will measure two different velocities of the wave relative to them, but they must agree on the wavelength. That's why that's like in big circle in the front of this board. Like no matter what, it doesn't matter what they're doing. Once the sound comes out of the motorcyclist, and that means like pressure pockets of air are separated by a certain amount, then no matter what's going on, like then the pressure pockets of air are being sent from the motorcyclist to your ear. They're flowing along, they're pulsing along, separated by like a half meter each or whatever it is. Well, it just doesn't matter if they're coming to you or you're going into them or who's watching what. If they're a half a meter apart, they're a half a meter apart. Every you, the receiver and the source are both going to agree on that. Now, they might not have been half a meter apart if the motorcycle were sitting still. Like the number might be different, and it is different from one case to the next. But within a case, once you set up the experiment, everybody in the experiment, in the phenomenon, has to agree on what the wavelength is. So if the source and the receiver disagree on velocity, well, let me back up. So if velocity equals wavelength times frequency, and the source and the receiver disagree on velocity, but they have to agree on wavelength, then they have to disagree on frequency. That's like what's going on here, is that we disagree on velocity. That's Galileo's principle of relativity. We agree on wavelength. Therefore, we disagree on frequency. And so then our experience is that you hear one note and I hear a different note, and we're both correct. If you put tape recorders down before the experiment started, like, and then you played the tape recorder, not you, whatever you guys, not tape recorders. How old am I? iPhones, whatever. You recorded them and then you put them down. When you're done and played them, they'd be two different notes and they'd both be equally right. So the punchline of the Doppler effect is two different frequency measurements that are both equally valid for any wave. In the case of sound, that means two different notes. The mechanism is that two different velocity measurements, and that happens because of Galileo's principle of relativity. And the computational technique is focus on the wavelength the whole time, because the wavelength is the one thing that everybody agrees on. Okay, so that's what we're going to do. That's what we did Monday. That's what you're going to do in a minute in breakout rooms. Um, okay, so that's like, okay, that's my summary. Now, okay, I'm going to throw in one last pitch on this, no pun intended. Because we're spending so much time on it, let me give you one little more teaser, sort of like the thing I'm about to say I think is interesting. It's not on the exam or anything like that. It'll be quick, sort of just as like another little teaser, like why was ist das Doppler effect? Like why is this so important to me? Well, like we're focusing it on sound because sound is familiar and real, I think. Um, but I keep saying that the Doppler effect applies to any wave at all. So if you assume for a minute, so here's just like an example of how important this is to the world. If you assume for a minute that there are certain circumstances where light behaves like a wave, and we're going to get to that, like that's the ultimate sort of goal of all this is why do we ever believe that? But we do. If you believe that sometimes light acts like a wave, the light waves that come from stars down to Earth, it turns out, as of like the middle of the 20th century, we have the technological capability to make very precise measurements of this light that comes down from stars to Earth. And with light waves, frequency, remember, with sound waves, frequency is interpreted as pitch, note, right? Like a 440 hertz sound frequency is middle A on a piano, or 256 hertz is middle C on a piano, if you know what I mean, right? But okay, with light waves, frequency is interpreted by the human brain or experienced by the human body as color. So like 1400 hertz. What am I saying? Sorry. I mean, like 5 times 10 to the 14th hertz. If you have light vibrating, whatever that means, if you have electromagnetic radiation vibrating, oscillating at a rate of approximately 5 times 10 to the 14th hertz. That's 500 trillion cycles per second. That's interpreted by the human brain as the color red, for example. Okay. And then higher frequencies are like orange, yellow, green, blue. You've probably heard this before. Why do I care? Well, because it turns out like we can measure the frequencies of light coming in from stars to the Earth. And not only can we measure them, but we can do spectroscopic observations of the light and determine and break down from the spectroscopic observations what the chemical composition must have been of the star that produced the light. And therefore, in fact, human beings possess the technological capability to gather a lot of really precise data as to what the frequencies of light, the colors of light would be as measured from the frame of reference of the stars that the light came from. I mean, this is very advanced. It's very impressive that now I haven't been doing anything, but like physicists have been, and astronomers have been doing this for now, like, 70 years approximately. So they have like a lot of data on this. Well, it turns out, and you may have heard this, but let me just reinforce, it turns out that the frequencies of the lights that are coming from stars, as measured or as understood what they would be measured in the star frame of reference, those measurements tend to be higher than what the frequencies are as measured in the Earth frame of reference. In general, there is what you may have heard of. There is something called the redshift of starlight, meaning that in general, when we measure frequencies of light coming from stars, we get smaller, like slightly, but consistently, like predictably, lower values for these frequencies on Earth than what we believe the values would be on stars. Lower values. Now remember, from the Doppler effect analysis we've done so far, if like when a source or a receiver of a wave is coming toward the other object, when you have source approach or receiver approach, we think of that as like you running toward the waves at the beach at Coney Island, and you experience the waves more frequently, right? When source or receiver approach, then the received frequency is higher than the source frequency. Conversely, when the source goes away or the receiver goes away, the received frequency is lower than the source frequency. Well, that's what we experience with starlight. We measure frequencies that are always more close to the red side of the electromagnetic spectrum than the violet side. I mean, we get colors, we measure them to be redder, closer to red than what we believe they would be in the star frame of reference. So this is why it's called the redshift, or sometimes it's called the Doppler shift of starlight. We believe, people have believed for like 70 years that starlight undergoes a Doppler effect as it travels from stars to us, but it experiences it in the low frequency direction, not the high frequency. Therefore, we infer, sorry. We infer that the source of these light waves, i.e., the stars, must be, in general, en masse, receding, moving away from us in general. We believe that the universe is expanding. You've heard this a million times. You've read it in the New York Times or whatever. It's a very weird thing to believe. But we believe that the universe is continually like enlarging, that things are getting more and more spread out, that stars in general are getting farther and farther away from us as time goes on. And we believe, ever since Galileo, that we are not special. We are not specifically any more than the center of the universe than anybody else is. So if everything seems to be spreading out from us all the time, apparently we believe, I mean, to the extent that we believe anything in science, when we believe with as much precision and confidence as we believe anything in science, we believe that things are getting farther and farther apart in the universe all the time. Why do we believe this? Because starlight reveals, demonstrates a Doppler shift, just like basically the stars are doing except the other way, except the other way around. I mean, so the Doppler effect ultimately, if you to understand and believe the Doppler effect is to understand or believe at least at core why we believe in something as crazy or unexpected and surprising as an expanding universe. I'm going to go one step farther now, just so you have perspective. If you believe in an expanding universe, which by the way, everybody does, I'm not saying they're right, but I mean, like most people just read this in the New York Times and like, okay, I guess that's what those crazy astronomers are up to these days. I mean, but it's like a very crazy thing to believe. I mean, don't even get me. I mean, I'm happy to talk about it in office hour. Like, let me put it this way: we don't believe in an expanding universe because we want to. It's not like something we came up with that makes sense. We believe in it because the data seems to demonstrate it beyond a shadow of a doubt. Like we believe in it because we think we have to because the Doppler data says so, say so. And go one step further. If you believe that the universe is expanding all the time, getting larger and larger, well, then just run that movie backwards in your mind. I mean, if the universe is always going like this, then that means at the beginning it was like this, right? And just like extrapolate backwards. If it's always going like this, that means somehow it started more like this. So if you go all the way back, presumably at some point, take it to the limit, it was like some tiny, tiny, tiny little point that exploded into all of this. That's where the idea of the Big Bang comes from. It's not the other way around. It's not like we believe in the Big Bang because we want to, and then we like roll out the tape from there and say, well, then I guess everything is getting bigger and bigger from the Big Bang. No, we think everything is getting bigger and bigger because of the Doppler effect. And then if you take that idea to its limit, it means everything started from a tiny beginning. Did I wake up this morning wanting to think that about the universe? No. I mean, maybe I do now because it's so exciting, but it's very weird, right? It's logical from the premise of the data and an understanding of the Doppler effect. I'm just so that just and that's just one taste of how fundamental the Doppler effect is to our way of understanding the universe. Having said all that, it's good. Thank God something's in the chat. Shut this man up, for heaven's sake. Is that also the reason? But I'm glad there's something in the chat, really. I'm glad you hung on to that. Wait, is that also the reason why when we look at stars, they say we were looking back into okay, I'm going to read this out loud. I mean, don't get me started on it. I mean, do get me started on this, but it says in the direct chat, is that also the reason why when we look at stars, they say that we are looking back in time, because the light waves that we receive are traveling such a long distance? Absolutely. I mean, you don't, yes, I fully agree with that statement. I love that statement. And I agree with it. And honestly, even that, like, you don't even need to fully understand all the nuances of the Doppler effect to get your mind around that. Or, well, get your mind around it takes a lifetime. But to get it, basically, that's correct. Like light. I mean, here I go. I don't really want, yes, like light, as long as you believe that light takes any time to get from one point to another, as long as you believe that light travels at a speed that is less than infinity, right? As long as you believe that light travels at a finite speed, which we do, then that means as long as no, no, no. I mean, it's a very cool point. It's a very cool point. And I just have to be careful not to like spend the rest of the class on it. But no, I mean, look, this is why we're here. Like, how could you not care? I mean, no, it's not I mean, it is a tangent, but no, don't apologize. Like, uh, this, oh, don't apologize. um, I just apologize to you if I don't get back on track in like 2 minutes. But yes, people, everybody, as long as you believe that light takes time to get from one point to another, and then that means as long as that means that light takes time to get from one point to another. So anytime you're seeing anything, even your teddy bear across the room, like honestly, I mean, it took like a millisecond or whatever for the light to get from the teddy bear to your eyes, right? So the teddy bear that you're registering in your brain is a teddy bear from a millisecond ago. There's literally no way around that idea. Like that just has, I mean, if anything, if distance equals rate times time makes sense, then that makes sense, right? Now you don't care because it's only your teddy bear from a millisecond ago. So like probably not much happened to your teddy bear within that millisecond. But yes, then if you're looking up at stars, it is absolutely true. The star that is closest to the Earth, other than the sun, the star that is closest to the Earth is a star called Alpha Centauri. You can't even see it from the northern hemisphere. You have to like go to Australia to see it. But even Alpha Centauri is already over 3 light years away, meaning it's so far away. You know what I mean? I mean, like it's so far away, even the closest one, that it takes light over 3 years to get from that star to us. That's the closest. A typical star like Betelgeuse, like a typical star that you see in the night sky, like in New York, like in the middle of winter, like if you see it, if you know Orion's belt or whatever, and there's a star right above Orion, whatever star, a typical star like Betelgeuse is like 400 light years away. That's not even extreme at all. That is totally like Midland average, 400 light years away. That absolutely means there's no way, this is not science fiction, and this is not philosophical extrapolation. It absolutely is the case that when you say, look how bright Betelgeuse is tonight, looking up at it with your friend, what you really mean is, look how bright Betelgeuse was 400 years ago. Absolutely. And if in the last 200 years Betelgeuse exploded, or like somehow, or which eventually it would do, like, or if it's not there anymore, you don't know that. You won't know it for another 200 years, if you know what I'm saying. Like, yes, you are absolutely, the farther you look into the sky, or the farther you look anywhere, the farther back in time you're looking. There's no two ways about it. And I'm not trivial. I mean, it's a huge point. It's a fascinating point. But that is just a matter of believing that light takes a finite amount of time to get from one place to another. Or put another way, that's just a matter of believing that light travels at a speed that's less than infinity. And by the way, that is not a trivial claim. It certainly doesn't feel that way. When you turn on light switches, it feels like the light gets there instantly. And people believe that for hundreds and hundreds and hundreds of years. It's a major breakthrough. It's a major head twister to discover and confirm that in fact light does literally travel at us. Forget what the number is. Who cares? I mean, I care, but just saying that it's a number at all is a major breakthrough of scientific progress that occurred in history. There was a huge amount of time in history where we did a lot of physics, a lot of science, made a lot of accurate predictions about the sky and the earth, and all of them just assumed that light just got there instantaneously, which is totally the way we think of it as little children, right? I mean, and not for I mean, for good reason. But no, once you believe that light takes any amount of time to get from one place to another, that means that whatever you're seeing is in the past. No two ways about it. And if that's not one of many, many reasons I think physics is cool, like I don't know what is. So it's not a tangent. It's like a reason to care about physics. But okay. But I am going to get back. Okay. So I'm going to put you in. So what you're going to do, here's the instructions that are completely illegible. I'm going to shut up. I always say that, and it's always not true, but I'm going to shut up. And we are going to take, and I'm going to sort of ask you to be sort of quick about this. What I'm going to ask you to do, I'm going to put you in breakout rooms. You're going to do a different case of the Doppler effect. The same number, all the numbers from homework 4, like the 800 number, the 80 number, the 340 number, the whole setup from homework 4. But on Monday, we did the case of the source approaching. You can look at your notes and follow the exact model. It's fine. But today you're doing, I mean, it's recommended, in fact. What you're doing today is the case of the receiver approaching, and you're going to solve for what you always solve for in the Doppler effect, the blue thing, FWR. Like everything else is given. You're solving for FWR in a breakout room in a minute. The only thing I'm going to then, but the only two other little things I'm going to ask you, and you are going to be fast. I'm going to bring you back. It may be faster than some of you. Like some of you might not finish. I just want you to try. So at least you're thinking about it and you're practicing. But before you start, I want you to predict. Like you can literally have your notes open from what we did Monday, and you're going to do the same method from what we did Monday. So predict in your group. Are we going to get the same answer that we did on Monday or not? Like, or is it going to be greater, or is it going to be smaller than what we did Monday? Okay, that just predict. This is not a test, this is practice, but predict whether the answer we get for FWR is going to be the same or not, or bigger or smaller than what we got Sunday. And then when you're done, if you finish fast enough, then look at your prediction. I mean, compare the two numbers and see if your prediction was right. Okay, I'm going to make breakout. So again, of course I'm always rushing at the end. I'm going to make the breakout rooms right now. And please go into your breakout room just immediately. I mean, give me a quick show of Is it clear, even if the physics is not clear, is it clear what I'm asking you to do in one moment as soon as I give you a breakout? Is it okay? That's one person. Wait, is it? Well, yes. Okay, two people. Thank you, director. All right, two is good enough for me. So here we go. Here come the breakout rooms. Again, it is going to be a little bit fast. I apologize. Here they come. Okay. So Kaya and Mariam, you want to go to breakout rooms. Are you there, Kaya? And oh, thank you. And Mariam, you want to go to breakout room? I'm gonna ideally we'd have a full discussion about this, but limited time, I want to make sure we at least get resolution on the answers. Very quickly, I want to ask you, first of all, sorry, would you raise your electronic hand if your group got an answer? Like if you had time to get an answer. Oh, is that no? Okay, raise your electronic hand if you did not get to an answer, just so I know what's going on. Oh, okay, wait, so you got to vote for one way or the other, please. Okay, so two, could everybody vote, please? I'm saying it, just raise your electronic hand if you did not yet get to an answer. That's most of you. Okay, okay. Well, I will get an answer. Hopefully, well, so we want to study this. I mean, you didn't have a lot of time. So hopefully it's just a matter like that you ran out of time, and I apologize for that. I'm going to show you the method again in a second, and I'll get you an answer. But I'm also curious. Could, well, or actually, let me ask this. I could do this in 11 minutes. If you just ran out of time, you ran out of time. But is there anybody who wants to share like where they got stuck? Like, did anybody literally get stuck somewhere and like not know what to do and have the is willing to share that just so I know? Like, can anybody identify where they got stuck, or is it just a matter that like the clock ran out? Brian, is that a or is your hand up from before? Or oh, okay. Is there anybody that wants to volunteer a place that they got stuck? Okay. Okay, Annie. Okay. Say, please.
So for my group, like we didn't really, it's a bit tricky because 12 of us weren't here on Monday to um experience the small group discussion. So we kind of just like chatted about like how we felt um about the last two questions where the receiver is moving towards the source or away from the source. And I think all of our answers are a bit different, but we ended up agreeing on the fact that if the receiver is moving closer to the source and the wave, like the sound waves, is coming from the source, then the receiver experiences or receive the sound at a faster rate, so the frequency should be higher. So we just agreed that the whatever number that you got for the scenario where the receiver is moving towards the source, that value should be higher than the other way around.
Perfect. Okay, that's super helpful, actually. Okay, That's super helpful for me to know where people are and everything. And yes, of course, and to everybody too, this also reinforces, like you could see, because I'm spending like 3 days on this, it kind of reinforces, it sends a message like you definitely all want to know this eventually, but it is very knowable. You notice, by the way, even though we're spending 3 days, it was not like calculus or anything involved in this. I'm not saying it's easy, but it's like concrete and digestible. This Doppler thing, like 4 cases, it's an algebraic approach. So, but of course, if you weren't here Monday, that would be this all should just suggest to everybody that please consult the PDF from Monday and the video from Monday. That will be very important. But okay, as far as what Andy said, substance, and I will go over, I've got 9 minutes. I will show you my example in a minute, and you will hopefully then in your leisure time, like compare my example of this to the example from Monday, and you'll hopefully see that they are the same method, even if they don't look that way. They are the same method, whether they get the same number or not. Now, one thing that Annie said that I definitely agree. I mean, everything Annie said, I agree. But one important thing is, yeah, if there is approach, if the receiver is approaching the source, or as it turns out, I'll just assert this, or if the source is approaching the receiver, either way, I agree. I would predict that the receiver will measure a higher frequency than the source will. In 2 out of 4 cases, when things are getting closer together, waves will be encountered more frequently than otherwise. So the receiver will measure a higher frequency than the source. And conversely, in the receding cases, the receiver will measure a lower frequency. Like that is what Annie was saying. That I agree. I'm going to go further now, but now the question is like Monday. Oh, and so for example, Monday, like in the numbers, the source measured an 800 hertz frequency, but the receiver we found on Monday, if you look at the math, the receiver measured like a 1048 or something, like over 1,000 hertz frequency. Very different from 800. As Annie said, it was higher than 800. And that's because the receiver was coming toward the source at like 80 meters per second. If it had been going faster, the frequency shift would be even higher. And if it does not go at all, then there's no frequency shift, if that makes sense. Now, today we're doing that was the source moving toward the receiver, and we got like 1048. Today we're doing the receiver moving toward the source. Andy's predicting, again, it will be higher than 800. I agree with the prediction. Now, but if I'm asked to predict, is my number going to be the same number that I got Monday? Here's the really subtle, difficult part. I'm telling you that I would predict, if I'd never done this before, I am telling you, and if I had been a good student of physics, like if I took very seriously the idea that all of this is about relativity being applied to waves, I would totally predict, I do every single time, predict that whether it's the receiver coming in or the source coming in, I would say, well, I assume it's going to be the same number. Like, first of all, I agree with Andy that it's going to be the same qualitative effect either way. The frequency will be measured higher. But furthermore, I would say, look, the whole thing of relativity is that it doesn't matter whether the Earth is coming toward us or we're going toward the Earth. It's the same effect on the universe. It doesn't matter whose frame of reference we look at. They're both correct. So I would have guessed, as it says on the board, I would have guessed that the case of the source approaching or the case of the receiver approaching, I would have guessed would get the same number, because I would think, who cares whether it's you coming to me or me coming to you? Relativity says VAB equals negative VBA. So that's what I would think. And I'm not trying to trick you. I'm saying this is one of the tricky, important features of the Doppler effect. I might think that there's really only 2 cases, approach and receive, and they're basically going to get, it's going to be 2 of the same answers and 2 of the same answers. But if I now do the math, I know we only 5 minutes. If I do the math that we did on Monday, what is the math approach? It's 3 steps. It's get the wavelength from the perspective of the source, realize it's really 2 steps. I mean, it's get the wavelength according to the source, realize that the wavelength according to the receiver has to be the same. So then use the wavelength at the receiver to get the frequency. It's just that all the way. So why do you get any two different frequencies? Because there's two different velocities. Why are there two different velocities? Because of Galileo's principle. In other words, here's the math with 4 minutes. I do. Wavelength of wave according to source equals velocity of wave according to source divided by frequency of wave according to source. How do I get the velocity of the wave according to source? I do the same thing I did on Monday. I say it's velocity of wave according to medium plus velocity of medium according to source. Same thing I did on Monday. Only this time, the velocity of the medium according to source, well, that's zero because the source is not moving in the air. This time, on Monday it was, in the other case, but here the case is that the receiver is moving. So that part is a zero. So I end up doing 340 over 800. I get that the wavelength of the wave, in this case, according to the source, is 0.425 meters. On Monday, to be clear, we did the same method, but we got that the wavelength was 0.3325 meters. When the, well, I'll go on for a second. But so I'm doing the same method, getting different numbers. Then I say, okay, this wavelength, everybody has to agree. What do I mean everybody has to agree? I mean, whether you're the source or the receiver, in this case, you're both going to agree that the wavelength is 0.425 meters. Again, notice, I'm not saying that it's the same number in all the cases. I'm saying within a case, everybody, source and receiver, within a case, perspective does not matter. They're all agreeing it's 0.425 meters. So then I go to the other page and say, okay, now I look at the receiver. To solve for the frequency of receiver equals velocity of receiver over wavelength according to receiver. How do I get the velocity of the wave according to receiver? And again, this is where every single time you'll notice the top of that fraction, whether it's substep A or substep B, the top of that fraction is a sum because I never explicitly know the velocity of the wave according to anything other than the medium. The only thing that's given that's known is the velocity of the wave in the medium. But so I do Galileo. I say, aha, VWR equals VWM plus VMR. What's VMR? The velocity of the medium according to the receiver. What the heck is that? That's like how fast the air is going according to the receiver. Why is the air going anywhere according to the receiver? Because the receiver is moving through the air. The receiver was moving against the wave at a velocity of negative 80. I say negative because whatever direction, like if you look always for every one of these cases, whatever direction the wave is going, I always make that positive. If you just look up at the yellow and the blue at the top, whatever way the wave is going, I consistently through all the cases make that direction positive. Therefore, if the receiver is approaching, it's going against the wave, it's going negative 80. VRM is negative 80. Therefore, VMR is the opposite of that. It's positive 80. Now, again, I have 1 minute left. That's where things like start to look very detailed and complicated. But what I'm trying to argue, if you sit down and look at this and you practice it, you will see you don't have to memorize any of these things. It's the logic of just setting up the coordinate system and following Galileo. You don't memorize, I mean, you can, but you don't have to. It actually just makes sense. Anyway, so the velocity of the medium relative to the receiver is 80 meters per second. So that's what I plug in. I say frequency of wave relative to receiver is 340 plus 180. In other words, that receiver's running into the wave. So it's coming faster at it than it is through the air. It's going 420. So, so that receiver measures a frequency of 988 hertz. With 1 minute left, punchline. I was wrong. I mean, not really, like my prediction was wrong. Apparently, whether the source moves or whether the source comes in or the receiver comes in, either way, you get a number higher than 800, but you don't get the same number either way. That's why we're analyzing all the four cases. You don't, because yes, this is all about relativity. Yes, it's all about relativity, but it's not about the source related to the receiver. It's about source related to medium versus receiver related to medium. In other words, the laws of physics are the same in all reference frames, but the medium is a reference frame that we cannot ignore. The medium is real. The medium counts as a reference frame. So in the end of the day, if this, so in the end of the day, the answer for source approach and receiver approach, they're both higher than 800, but they're different answers because in one case the source is moving relative to the medium, in the other case the receiver is moving relative to the medium. So we'll stop there. You've been very patient. I will see you. Oh, what does it say in yellow? What does it say in yellow? Sorry, it says, I think that's just a picture. You mean there? It's just like a picture of a speaker making sound and the ear. Sorry, you can all go. But I mean, you don't have to. I'll answer your questions. But I think that the yellow is a picture of the speaker and the receiver coming toward the speaker. Is that what you're asking? Wait. Oh, back to the prediction. Oh. Sorry. It says, thank you. Oh, thank you. Wait, I'll turn off the recording. Hold on. Sorry.